Professor Yann LeCun is a French computer scientist known for his pioneering work on convolutional neural networks, optical character recognition, and computer vision. He's a Silver Professor at New York University and Vice President and Chief AI Scientist at Meta. Alongside Yoshua Bengio and Geoffrey Hinton, he was awarded the 2018 Turing Award for their work on deep learning, earning himself the nickname as one of the Godfathers of Deep Learning. Enjoy.
Lovely to see you in person. So we had a great conversation with Ishan and Randall earlier about the self-supervised paper and also the data-augmentation paper.
Right.
I just wondered if you had any thoughts on the papers.
Well, so Randall has 4 papers that he co-authored at NEURIPS, which is kind of very impressive. All of them kind of somewhat theoretical, but all of them really having an insight that's really important, really interesting. One of the ones that was presented today is actually on unitary neural nets. So these are neural nets where the weight matrix is forced to be a unitary matrix, basically a form of rotation in complex space. And that has some advantages because it solves some technical issue with either exploding or vanishing gradient. And also it can be seen as sort of a model of quantum computation. In fact, the main author, Yann, is a quantum computer student at MIT, with Seth Lloyd, who is the last author of the paper, who is one of the best known people in quantum computing. So that's a very interesting paper. It makes the idea of training unitary matrices efficient. Then there is the paper also that was presented today on some analytical study of what data augmentation does for you, right? So you can take an image and you can transform it in various ways, and the number of different ways in which you can transform an image, is kind of quasi infinite.
Yeah.
And it turns out, if you take the limit to infinity, you get some sort of formula that you can actually solve. And so basically, you kind of see the effect of that would be equivalent to having an infinite number of data augmentation for a single sample.
Yeah, that reminded me of the kernel trick, actually.
A little bit,
It's a similar kind of concept.
Actually, the thing that reminds me of is some work that Patrice Simard did at Bell Labs many, many years ago, which I was a co-author as well, called tangent propagation and tangent distance. So this is really kind of closely related to that, but it's interesting to kind of see those ideas coming back to the fore. And then another really interesting paper from Randall is about, basically when you do self-supervised learning with data augmentation, you have a large number of training samples, and then you distort them, and you view distorted version of the same sample as being similar or identical, and then different samples to be dissimilar. And you can view this conceptually as a big graph of similarity, where you collect all the samples and their augmentations, and then you build a gigantic matrix, if you want, where you put 1 if they are similar, 0 if they're not. And what Randall figured out is that what's important are the spectral property of this matrix, so basically its eigenvectors, eigenvalues, in relation to the spectral properties of a similar matrix that would correspond to for example, a supervised task. Okay, so the self-supervised task, surrogate task, if you want, is going to help to solve the supervised task to the extent that those 2 matrices have matching spectral properties. You could say it this way.
Indeed. I had a question about that. So in a way, the creating that adjacency matrix is a hypothetical to tell us about the representational capacity of self-supervised embeddings. But what does it mean for self-supervised learning in general if it feels like we need to have the class labels back to create that adjacency matrix?
Well, so you don't have it, right? I mean, you make the hypothesis that you don't have it in the pre-training phase, of course. But what the result tells you is the surrogate task that consists in distorting your images or whatever it is that you use in the self-supervised phase, it will help the final task to the extent that the eigenvectors of the 2 matrices have some overlap.
Interesting. And how do you think now, because in the Dino paper, Mathilde had a diagram which was speaking about the pointillistic nature of supervised learning. And OpenAI recently released a bit of a slightly combative paper, Whisper, where they were kind of saying, well, supervised representations are very robust out of distribution. So I just wondered, what's your current thinking around the robustness of self-supervised representations?
So I think, ultimately, I think self-supervised methods that use multiple criteria are going to be the main method to pre-train neural nets before we train them for a particular task, right? And the trick is, I mean, the big question is, can you build those surrogate tasks without requiring expensive manual labeling? Mm-hmm. And this is what data-augmentation does. It's just a way of generating labeled data, if you want. Yeah. Which is not really labels, but it's kind of similar. Yeah. Without requiring human intervention. So are there other tricks you can use that are similar to that would drive a system to learn the right things? Yeah. And the answer is not clear at this point, but the ideas have been floating around for a long time, including in computational neuroscience, like slow feature analysis, for example. So the hypothesis that the representation of 2 frames in a video that are successive or nearby should basically be similar because they probably contain the same objects, perhaps in slightly different positions, but the essential content is the same. So if you have a criterion that tends to produce similar representations for nearby frames, then you probably have a good criterion for extracting kind of relevant features about the world. I'm sort of becoming a much bigger fan of prediction. Mm-hmm. So observing temporal or spatial evolution of a phenomenon and then training a system to predict.
I'm a huge fan of your paper, by the way, The Path to Autonomous AI.
Right. So that's all based on this idea, right? Of prediction. And to some extent, all the papers that we're seeing right now on self-supervised learning based on masking are essentially versions of this. So you take an image, a video, a piece of audio or something, and then you have a corrupted version of it where some pieces are missing that you show to a network, and then you try to get this network to predict the parts that are missing, essentially. Yeah. So you can do this in a generative way, which is what masked autoencoders and denoising autoencoders are doing. That works really well in NLP. It doesn't work so well in images. I mean, there's NAE, which comes out of FAIR, which works okay, but it's difficult to scale. It doesn't produce like really good features. You have to like fine tune for the features to be good. But it has this idea that you mask a piece and you predict the part that is not masked, right? Yes. Now, what I've become much more fond of now is not generative models, but what's called joint embedding architecture. So all the best SSL method for images use joint embedding. Yeah. You have
as it's non-contrastive.
Well, so then you can use either contrastive or non-contrastive method to train them, but I'm advocating for non-contrastive because I think contrastive methods don't scale very well.
Could I touch on that? Because Randall and I were joking about the not quite rivalry with you and Geoff going back many years, and because I think even to this day, you said in your JEPA paper that the non-contrastive methods are a way of shrink wrapping the latent space around the data.
That's right.
And I just wondered, has your thinking changed about that? And what would you say to people who still think that it's possible to achieve good results with contrastive learning?
Well, I mean, you do get good results with contrastive methods. It's just that you get results, and we've shown this in a number of other papers, that the part of the space that is occupied by the representation is relatively low dimension. Yeah. So it's kind of a dimensional collapse. Yeah. That's what we call it, actually. And so you train contrastive methods like SimClear, for example, and the type of representations that you get spans a relatively low dimensional subspace of the representation space. And so that tells you that when you want to kind of push things to be different and you are in a high dimensional space, you're kind of, the number of negative pairs that you need grows exponentially with the dimension of the space, essentially.
Yes.
And so that's what makes me kind of dubious. But then we have a paper on arXiv. Randall is co-author as well, actually, where this is a paper by Quentin Garrido, who is a PhD student with me in Paris, and that shows that there is actually some sort of duality between contrastive and non-contrastive methods. Mm-hmm. In contrastive method, what you're trying to do is make sure that the representations produced by the system for different samples in a batch are all different, right?
Yep.
So you take a matrix of representations, you're trying to make the rows of that matrix different.
Yep.
Non-contrastive methods are actually contrastive, but they're contrastive in the other dimension, right? So they're trying to make all the variables of a representation different. And so one deals with a covariance matrix, which is Z times Z transpose, and the other one is Z transpose Z. And those two matrices have the same eigenvectors, the same eigenvalues, so or have common properties. And so there is a duality between those two methods, which seems to invalidate the argument I have that. So we're still kind of trying to go through this and try to really understand what the story is there. But ultimately, I think non-contrastive methods are the way to go.
Fascinating. Just quickly finishing on Geoffrey. So I was speaking with Sepp just a little while ago, and he also agrees with you, I think, which is that the ability to model phenomena at multiple levels of abstraction or description is really, really important.
Right.
And also, doing it with the joint embedding prediction architecture on the latent space, also action space abstractions in time as well as concept abstraction. Yes. I was a huge fan of that paper. It's very, very interesting. But the other thing, of course, it did was introduce uncertainty quantification as part of the predicting what is not observed from what is observed.
That's right.
So but I mean one thing I did think at the time though is that it does start to resemble a handcrafted cognitive architecture again.
It is, yeah. That's what it is. It's a cognitive architecture.
Well, what would Rich Sutton say?
I don't know what Rich Sutton say. He's co-author of this paper. Reward is enough, right? I mean,
I'd love to get your thoughts on that.
Well, in my position paper, I say reward is not enough.
I know it's not. Yeah.
I mean, I think actually, I say this as like a half a joke, but I think the purpose of reinforcement learning should be to minimize the use of reinforcement learning, because reinforcement learning is so damn inefficient. Pardon my French.
Yes.
So in fact, I think whenever possible, we should be using something like model predictive control or something like that, which is way more efficient, like planning. Okay, yeah. Which is a sort of more classical AI type approach.
Yeah.
But which systems like mu0 use, and some systems that I've worked on with former student of mine who's now at FAIR, Michael Enaf, for autonomous driving, for planning trajectories and stuff like that. And there's a lot of work going back quite a long time on planning. I think that's frankly this idea that sort of intelligent system should optimize an objective by planning a sequence of actions or a sequence of, it can be text or whatever. That's what would make those models controllable, whereas currently they really are not. Like it's very hard to control a language model to do something particular, other than by feeding it a huge prompt, which really is a bad way of specifying a task.
Indeed.
So, and then the thing you mentioned is the ability to represent sort of hierarchical action plans.
Yes.
This is something that no AI systems today can do.
Yeah.
And I think it's a super important problem. I don't have a complete solution for it. I just have a hint of a solution, which I present in that paper. But I think that's kind of a major obstacle to clear.
Interesting. On reward is enough. I think there are different ways of defining intelligence. So there's behavior, there's function. Does it do planning and reasoning, like Norvig would say. There's capability. There's principle, which is I think that some of these folks who think reward is enough, that they have this idea that an intelligent agent is just taking the right trajectory of decisions, Bayesian optimal decisions, if you like. And I think that's where a lot of this kind of thinking process stems from. Would you agree with that, or do you have a different conception of intelligence?
So I think, there is certainly, okay, let's take a simple problem of classification. When you train a classifier, the real function you want to minimize is classification error. But we never do this. We always come up with a surrogate objective that we optimize that happens to be differentiable, because number of errors is not differentiable, right? So you approximate this with cross entropy or whatever, right? And then you can do gradient descent, and that's the success of deep learning, is to basically say, look, we can optimize the stuff we want to optimize. We can find those other objectives that are just as good, and we optimize those with gradient-based methods. So reinforcement learning is the application to control of this idea that you have an objective you want to minimize, but the problem is that it's not differentiable.
Yeah.
You only get this value once in a while. to estimate this gradient, you have to take multiple actions to see, a policy gradient, basically to kind of see how it varies when you change the action, so that you can perhaps find a minimum. And that's a very inefficient way of optimizing anything that learns. So what you should have is have a surrogate cost that is a good approximation of the cost you actually want to minimize, but is differentiable. And if it's differentiable, then you can use gradient-based methods to do planning. You don't have to learn a policy.
Yep.
You could learn a policy, of course, and then that becomes what people call optimal control, which has been around since the 50s. It's a neural net version of it, if you want, but it's the same sort of overall framework.
Yeah.
That's what you should do whenever you can. I mean, the same way nobody ever trains a neural net using gradient-free methods to minimize classification error. Nobody should ever use RL. People should use optimal control with surrogate costs that are differentiable that approximate the cost you actually want to minimize. Now, of course, you can't do this approximation exactly. So once in a while, you have to discover that your surrogate cost is not the right one, and then you have to adjust it, and that's RL. But presumably, you would have to use it extremely rarely, right? So,
Indeed.
So again, the purpose of RL research should be to minimize its use.
Amazing. That's a wonderful take. I don't want to take up too much more of your time, but I wanted to quickly come back to Randall. So first of all, Randall is one of the most talented researchers that I know of. He has, I wanted to just get your comments on what it's like to work with Randall, but also his spline theory of neural networks I find particularly interesting, And also, he's recently, because I guess, it all started with your extrapolation paper.
Right.
And then we discovered Randall's work as a byproduct of that. And our initial reading of Randall's work is that, in respect of an input example, a neural network can be represented as an affine transformation. And we were kind of thinking that this almost reinforces the idea that neural networks are locality-sensitive hashing tables and they don't extrapolate. And my conception at the time was that all of the inductive priors, like for example the CNN, what it does is it photocopies the input data. It kind of it spreads it out over the ambient space, and then we have these polyhedra that capture all of the photocopies. But now Randall has said, well, actually, in contrast to decision trees, they are extrapolative because these are continuous regions, and they make very informed. They give you very informed information about extrapolative regions that were not seen during training, and that actually explains a lot of the extrapolation.
That's true. Yeah. I mean, it's kind of the similar argument that people had when comparing. Back in the old days, comparing like nearest neighbor classifiers to linear classifiers. A linear classifier, puts a boundary, and outside of that boundary, it extrapolates. You can think of it this way, whereas nearest neighbor doesn't.
Yeah.
Or at least not nearly in the same kind of same respect. So,
Fantastic. And just a quick comment on what it's like to work with Randall.
Oh, it's fantastic. It's very productive and comes up with lots of theoretical insights and things like that, and you don't need to give him ideas because he comes up with tons of them. But if you give him one, he's going to run with it. So
amazing.
It's wonderful to work with.
Yann, it's a pleasure to meet you. It's a pleasure to meet you. Thank you so much.
So it becomes a constraint optimization problem, and this is exactly what you obtain and you recover Laplacian eigenmap from the Craig. So it's the same loss function. And it's just that it's a non-parametric regime, right?
Okay, so I'm just taking a little bit of time to chat with Randall.
Thanks.
And today's the big day, actually. You're doing a poster.
Yes, first of 4, actually. So it's going to be warm up for me. But today is a really interesting one on self-supervised learning, tying it to spectral embedding, and trying to understand in a more principled way when does it work, when does it fail, and when can you unite actually those two sides of the same thing.
Fantastic. Well, give us the elevator pitch of the paper.
Sure. So the main idea is that now you have a ton of different self-supervised losses, right? Many different variants, and it's not clear how to navigate this space, right? Given a new problem, new data set, which loss do you want to use and why? And so what we do in this paper is that we actually tie most of those losses to known spectral embedding methods. We show that it's exactly the same loss. We have the same optimal representation. You can find things analytically and prove this already. And from this, we can use the rich literature of spectral embedding to tell you when, in which type of data distribution is one loss better than the other, and what type of properties of your data does one loss try to care about compared to those other losses? So by doing this very simple bridge, then we can get a big insight into guiding practitioners basically in which loss to use, when, and why. And so this is the main bulk of the contribution. And another one is that through this bridge again, we see that the main task of self-supervised learning is to design a good relation graph, basically. So if you have a lot of data points, when you define a positive pair, what you say is that, okay, this sample and this sample are positively related to each other. And this, if you look at your big graph of data points, you add a connection between those 2 points. Mm-hmm. And if you know how to put those connections correctly, then you can actually learn optimal representations. And for example, if you do supervised training, the only thing it means is that you already know where to put all those connections because you have the class labels. But you see, you have the same unified viewpoint for supervised training, SSL, and you can try from this to understand how can you maybe interpolate between those 2 regimes. You can try to say, okay, can you do better ways in finding which pairs are connected? Mm-hmm. And if you know how to do this efficiently, you can, for example, get rid of data augmentation altogether to define your positive pairs and so on and so forth. So hopefully this opens a lot of doors for future work.
Oh, that's really interesting. And if there are multiple classes, then you just add multiple entries into that.
So in this big n by n matrix, n being the number of samples you have, if you have, let's say, 3 classes, this just means that you have 3 blocks in this big matrix, connecting all the points from class 1 together, all the points from class 2 together, and all the points of class 3 together. So I actually put some illustration of this in the poster, so you will see that later. But you can really, from this unified viewpoint, you have a graph, same thing in both cases. Yeah. You can tackle supervised learning, multi-class or not multi-class, SSL, and you can see in between what's happening. Even semi-supervised learning, where in this case, you only know some labels for some of the samples, and you already know the entries of these big graphs, this big matrix for those specific ones. Mm. And then the question is, okay, what do you do with those other ones? And here you have many methods, and one thing you could do, for example, from this, is that you could use self-supervised learning for those other guys. And we show how you can do this probably, basically, not just by combining losses without any guarantee.
Interesting. So devil's advocate, from the perspective of data augmentation, that's a really interesting way to encode more prior information into the predictive architecture. Yeah. So what if I was to suggest that we need that prior information and we're losing it somehow?
Yeah, so that's a good point. So if you add some prior, this is good as long as you know which prior to add, right? And one problem with SSL now is that if you remove some of the data augmentation, you have a big drop in performance and you have some collapse representations that appear. Especially, for example, color jitter if you have images. And one thing that you could do if you mix, specifying only some of the data augmentation, but also enabling to discover some other ones from the data by figuring out how to pair the samples, then you can try to have the best of both worlds, right? Mm-hmm. And suddenly you can come up with new augmentations naturally by pairing those points that you could not come up with just by trying to define a data augmentation, in PyTorch or whatever. And so one method that already tries to take a step in that direction is NNClear, where basically, so it's an extension of SimClear. It's really recent, I think 2 years ago it appeared. And what they do is that they look in embedding space and they look at the nearest neighbor of the samples to define which ones should be your positive pairs. Mm-hmm. So if you remember this big n by n connection matrix, what it says that, okay, this point, I will figure out to which other one is it connected to, based on the nearest neighbor in embedding space. And so you see, this is really a first step toward the automated discovery, let's say, of knowledge. And because of this, now they can get rid away of misspecifying the data augmentation pipeline. So for example, they can just use random crop, so really not too informative data augmentation pipelines. And naturally, because of the nearest neighbor pairing, you will have rich enough positive pairs that you can learn really good representation, reaching state-of-the-art performance, basically. So the goal here is to show why this works, why is it meaningful, and to improve this from first principles, basically.
Amazing. And by the way, we're huge fans of the original SimClear by Simon Cornblyth. That was one of our favorite interviews that we did. But this also brings me back to, we were discussing yesterday a little bit about the history of contrastive versus non-contrastive learning, and you're actually saying that there is rivalry is too strong a word, but there's a bit of an interesting background to that with Hinton and LeCun.
Yes, yeah, exactly. So rivalry maybe is a bit too strong of a word, but let's say two different objectives basically that led to those two big directions. So Hinton, so 20, 30 years ago, was trying to use this contrastive, so really close to SimClear type of criteria to learn new transformation of your space, so that in this new space you can do k-nearest neighbor or k-means in a better way. And the goal was really to have a nice metric space, and because of this you need contrastive style learning. And on the opposite, you had Yann that was trying with Siamese networks to learn representation close to each other for inputs that are in the same with the same class labels, basically, or semantically correlated. And basically, it was non-contrastive, just trying to match the representation from Siamese type model. And this was also 30 years ago, right? This was for like signature fraud detection. And so this emerged like 30 years ago, and you have those two big siloed, let's say, views that continue to improve until what we have today. So it's really nice to see the evolution, basically. And I would say, so this was maybe the origin of this whole path. In between, you had, let's say, increase of spectral embedding with kernel method at one point, maybe at the end of the 90s, 2000. And this is where you had Laplacian eigenmap, local linear embedding, all those things, right? And then after this, now you have again the rise of SSL, where they said, okay, let's remove the kernel method. Let's instead use DeepNet as a futurizer, but still the same sort of criteria, right? Which is what we show in the poster. And now you get those really nice, regime where you can actually extrapolate, and it's also efficient for large data set and so on. So it's really nice to see this evolution through the last 3 decades, basically.
Yeah, absolutely. And I was reading on Yann's take of contrastive versus non-contrastive in his recent autonomous AI paper, and he was describing the benefits in his view of non-contrastive methods is kind of shrink wrapping the latent representation. And you had a bit of a spicy take yesterday where you're saying you're now slightly more skeptical about the need for that.
Yeah, so I think it really depends on the situation that you are in, and that's one of the guidelines that we try to show in this paper. Basically, you have some properties that will be preserved with contrastive and some other with non-contrastive. And depending in the situation you are in, you may want to use one or the other, but there are cases where actually the representation will coincide between those two. So it's not a white and black story. It's really, you have like a spectrum, let's say, and in some regime, it does not matter which method you use, you will learn the same representation. In some other cases, you might prefer one from the other. And this type of question, you can only answer it theoretically because you cannot do huge scale experiment of thousands of data sets, thousands of architecture and so on. And this is what we try to do in this paper.
Amazing, amazing. Well, we're here at NEURIPS today, and this is the kind of the booths area where a lot of companies can demonstrate what they're working on. And you're going to be doing a poster session next door.
Yes, this afternoon. Yeah. For tomorrow and the next day. So feel free to come by.
Yeah, I mean, it's actually insane. Randall's got so many papers that he's presenting.
Yeah, I got really lucky, but it's really easy when you have Yann, throwing so much ID nearby. So you just have to pick up on them and basically work them out. So I cheat a little bit on that front.
Brilliant. Well, we're on day 2 of the conference. I mean, do you have any thoughts on what you've experienced so far?
So far, I think the organization is pretty smooth, and the posters all is really well organized, so we can walk around and figure out which paper are interesting. You just have to be patient to be in the queue for food, basically. That's the only downside. And also, if you like boats, we have a lot of workboat advertisements somehow nearby, so this is a bit intriguing as well, But except that, no, I think everything is going great, and a lot of people are, I think, really happy to be here. I met a lot of people who don't really have any paper or submission, but still were able to come. And I think everyone is excited. For many, it's the first in-person conference this COVID. So I think everyone is really cheerful and happy to share their research. So far, it's really nice.
Yeah, all right.
Great to see you. Give us the elevator pitch.
Right, so this is paper primarily done with Randall and Yann. And in this work, we really study the effect of data augmentation and how it can basically affect the model's parameters and a loss function. Now, typically, when people do this, there is no real understanding of how data augmentation affects this loss, apart from really just like sitting and training this. And you can think of this as a Monte Carlo estimator where you're actually drawing samples from this distribution of data augmentation, and you're trying to figure out how it affects the loss function or the model. This is one of the first works to actually show an analytical closed-form way of studying the effect of data augmentation on model parameters. And to the best of our knowledge, it's one of the first works also to do this for a wide range of data augmentations practically used in computer vision, like color jitter, Gaussian blur, affine transforms. And what we actually show is that you can think of all transforms as an operator on top of the image. We compute the expected image, the variance image. It leads to like pretty cool visualizations. Also understanding why data augmentation makes the model focus on textures or edges. And then finally, we show a closed form update of models when using a certain family of data augmentations. So yeah, that's it.
How are you finding the conference?
The conference has been good. It's actually been really diverse compared to like, I'm used to attending CVPR. So this is one of the conferences where I actually get to see lots of other ideas, lots of other fields. And it's been really fun.
Amazing. Ishan, it's such an honor to meet you in person.
Thank you.
Ishan is without a doubt one of the world's leading experts in computer vision. So it means so much to me to meet you in person.